So today I'd like to talk about climate change, climate warming, and I'll do it, of course, as a scientist, as a physicist. The main question we shall discuss today is, are we experiencing a continuous and gradual temperature change that would bring us to higher and higher temperatures? Or instead, are we facing a nearby tipping into a new, hotter and unknown state from which it should be very difficult to come back? So that's the program. Let's go. Well, so the title of my talk is Climate Change, Drifting or Tipping. And we shall discuss in details in this talk the answer of physics. I'd like to illustrate this title by a couple of images. Here we have a kayaker who is paddling down a nice river, a powerful river anyway. It turns out that the current velocity, the flow velocity increases minute after minute, but he's a good kayaker and he knows that whenever he wants, he'll be able to turn back and paddle against the flow. But if he does not, he may be facing another situation, which is this one. And at this point, if he decides to turn back, I presume it will be slightly more difficult than in the previous case. So this is drifting and this is tipping. You see that drifting is reversible, tipping is not. And there is some similarities between kayaking and climate, because in the case of kayaking, the kayaker usually walks along the river before starting his trip and explores whether he finds rapids or waterfalls or whatever. Of course, for climate this is not possible, and a climatic kayaker navigates paddles with blind eyes. That's a bit worrying. Well, so the contents of my talk are here. An introduction where we shall discuss where we are staying in the present time in terms of climate. And then two big chapters. The first one deals with complex systems in the physical meaning. And I shall show that in such complex systems, such systems may exhibit quite particular behaviors like tipping points and collapses. And then in the following chapter here, we shall apply these findings to climate, which is an emblematic example of a complex system. And then we'll go to a conclusion. Right. So let's start with the introduction and with the question, where are we staying? This is the Earth, typically 12,000 kilometers in diameter, and an atmosphere which is less than 12,000 meters thick. This means that, the depth of oceans are the same order of magnitude, of course. And if the Earth was 1 meter in diameter, then the atmosphere would be less than 1 millimeter thick. So we are living in a very, very thin and delicate layer around this sphere, and this is unfortunately the case, precisely the case, the place where we are discarding all our waste. And that's more than worrying, of course. So this is geography. Let's have a few words on history. The history of Earth temperatures, of atmosphere temperatures. We start here a very long time ago, 500 million years here, and we go to present times there. Be careful to one thing, the time scale is not linear at all. You have here on the right 1,000 years, on the left million years, and every vertical white line indicates a change in time scale. So be careful about this point. A few milestones. So here minus 500 million years, Here the PETM, which is the Paleocene-Eocene thermal maximum, in which temperatures raise to a significant level there. And then what else? Here, Lucy, our ancestor Lucy. And then these are the oldest ice-core records we have, 800,000 years. And finally, we come to this point, which is the beginning of a fairly stable period in terms of temperatures, stable within plus or minus 0.2 or 0.5 degrees. And this is the period in which our human civilization developed. It started 11,000 years ago at a point where our ancestors were hunters and gatherers and tend to be, I should say, farmers. And then these stable temperatures allowed the human civilization to develop and to bring us to the state we are living now. And now if we were able to concentrate, to zoom on this part here, which is only the last 150 years, since the beginning, the middle of the 19th century up to present times, we should observe a steep increase of temperatures far beyond these fluctuations here of plus or minus 0.2, 0.3 degrees. Here the dashed brown line is at plus 2 degrees as compared to this reference here, and the white line is at plus 4 degrees compared to the reference. Such warmings have not been experienced by human civilization, because plus 2 degrees, to find plus 2 degrees in the past, we have to come back to this point here at 130,000 years ago, 130,000 years ago, so well before our civilization. And if we take the plus 4 degrees warming, it brings us back to several million years. So when people tell you, well, that's climate change is not important, is not frightening, because we already experienced such warmings in the past, followed by cold periods, and everything recovers quite frequently and easily. That's totally wrong, because it did not happen a single time during this civilization period. We humans, civilized humans, did not experience such elevated temperatures. So this is scary, actually. Another historical point. This is the evolution of greenhouse gases concentrations. Actually, CO2 in ppm here during the last 2,000 years. So you see that the concentration was stable for a very long time up to this point. And this point is the beginning or the middle of the 19th century, the beginning of the industrial era. And then from this point, the concentration in CO2 is skyrocketing here. And I mention here this thin yellow line, which is the creation of IPCC in 1988. IPCC is the International Panel for Climate Change. And you may notice that if you compare the skyrocketing curve just before and just after IPCC creation, there is absolutely no change in the trend. So this means that whatever the publications of IPCC, decision makers do not care at all of these warnings. Finally, a few projections. These curves are taken from the Meadows report published in the MIT by a group of 4 researchers in 1972. The Meadows report was here in 1972. These are the present times, 22, 23. and these are the curves for life expectancy, population, food per capita, resources, and so on. So at those times, at the time of Meadows' report, everything seemed to be okay. But these people noticed that the resources curve was declining, was decreasing slowly. And if you combine a decreasing tendency in resources and a growing population, then something has to happen. And the result is a maximum in life expectancy, which decreases then rather fast, a decrease in population, a decrease of food per capita, and so on. So these were the predictions of the Meadows report, and these nasty things were predicted to happen after 2022. It's just the present period. Well, so now let's go to simple and complex systems. I shall start with a short experiment here. I take a rubber band and I stretch it. As I stretch it, it elongates. If I stretch it a bit more, it elongates a bit more. But if I go on too far from the initial state, then at some point the rubber band may fail. So this means that continuous loading, in the general meaning of the word, if the continuous under continuous loading, increasing loading, then something may happen here, which is a failure, which is a tipping point, as I shall explain in a moment. Now, second point, another experiment, maybe a bit more interesting. We take a fabric made of tightly entangled fibers with a crack, and we load it in tension vertically, more and more we're increasing the load, and at some time one of the fibers may fail, and the crack size may increase a little bit. And we go on increasing the load, and then another event occurs, which is that instead of one fiber, you have a group of 3, 4, or 5 fibers that fail more or less at the same time as a small avalanche of failures, and the crack size increases as well, and so on, up to a moment where the number of fibers that fail at the same time in this kind of avalanche reaches the size of the fabric, and this is called the tipping point. So two interesting things. In a tipping point, the tipping point is defined by the fact that the avalanche size reaches the system size, and the second point is that this tipping point is announced by an increasing number of avalanches, of fiber failures, of larger and larger intensities. Now, from Newton to Poincaré, these are two famous scientists. Newton first derived the well-known gravitation law here, and to derive this law, he considered the interaction between an apple and the earth, and he neglected everything else. He neglected the bugs running in the grass, or the tree leaves shivering in the wind, and so on. And simplifying the system so drastically, he could find this famous law, which is quite a simple model, but still valid, of course. On the other hand, Poincaré here, who was famous as the father of the deterministic chaos theory, Poincaré showed that when you have a system complex enough, made of a large number of elements with strong mutual interactions, then you should be able to describe the system by very simple models as well, of a different nature, but simple models as well. Going further in these complex systems, well, they are made of a large number of strongly interacting elements, as I said, and they are characterized by the fact that you observe the emergence of a global macroscopic behavior which is missing at the individual element scale. Good example is this one, a sheep flock, a sheep herd, and everybody knows that the properties, the behavior of the sheep herd is quite different from the behavior of single animals. So let's start with a widely spread flock. So the average distance between animals is fairly large. And then when one of them falls down, for instance, then this event may influence maybe 2 or 3 animals around it. But now if you gather the flock a bit more, the same event will influence a larger number of animals, maybe 10 or 15, and so on. As you gather more and more, what's called the correlation length, which is the size of the group which is influenced by the single initial event, increases. And at some time, this correlation length reaches the size of the herd. So this is the tipping point, because when an animal falls down in this situation, in this close to critical situation, then the whole herd may be influenced by this single event. A few examples now. While approaching the tipping points, the approach of a critical point is announced by increasing jolts, as we said a moment ago with the fabric. So, and the tipping occurs when the correlation length reaches the system size. I insist on the fact that these things are perfectly known since a long time in theoretical physics, but sometimes not often used in other fields of science, and this is a pity because it's a very, very powerful tool. Coming back to examples, as we saw just before, in a sheep herd, when the sheep jumps off a cliff, then the flock follows if the system is in a close to critical state. Tearing a fabric, if an extra fiber fails, and if we are in a close to critical state, then the other ones fail, and the fabric is teared into 2 different parts. Snow avalanches, also in the same conditions of close to criticality, I should say. 6 skiers crossed the slope, and they said to the 7th one, "It's okay, nothing happens." Well, actually nothing visible happened. And the 7th one proceeds, and the avalanche is released. In the case of landslides, well, the equations are the same as for snow avalanches. You have a slope in which 4 houses, for instance, are already built, and you build a 5th house, and then the whole slope flows down. These are mechanical examples, but these models, the theory applies to quite a wide field of scientific field. For instance, war outbreaks. You remember that the assassination of Archduke Franz Ferdinand in 1914 triggered World War I. But actually, this assassination was just an extra event in a lot of previous events. The system was already close to critical, and this assassination was the last fiber that failed and triggered the whole thing. I can give you lots of other examples. For instance, civilization collapses, Mayas here, and Nassau's and Easter Island, in which all these systems were brought to close to critical state, and then something, an extra event happened, and the civilization collapsed. I'd like to mention that in all these cases, there's a common thread, which is the incompetence of decision makers. Well, just a remark. The stock market crashes follow the same laws. If you are interested, you may type these names on the internet, and you will have very interesting analysis. So let's go to the next chapter now, climate as an emblematic example of complex systems, of the behavior of complex systems. So this is an illustration of the greenhouse effect here, where you have solar radiations, which are short-waved solar radiations that heat the interior of the greenhouse, and this heated system emits in turn long-wave radiations, infrared radiations, and the greenhouse effect relies on the fact that these long-wave radiations are stopped by the roof, which is not the case for short-wave radiations. What are the main greenhouse gases in Earth, in the Earth atmosphere? Maybe the most important one is H2O, water vapor, which is actually self-regulated. If we had no water vapor in our atmosphere, then we should experience very, very cold temperatures, and we wouldn't be here to discuss this point, of course. But this greenhouse gas is quite interesting because it's self-regulated. What I mean is that water is present on Earth through three different physical forms: solid, ice; liquid, water; and vapor, water vapor. And these three phases are in equilibrium on Earth, which means that if you introduce an extra amount of water vapor in the atmosphere, which would increase the greenhouse effect, you push the system out from its equilibrium, and it reacts by rainfalls or snowfalls in order to restore the right amount of water vapor in the atmosphere. So this is a self-regulating process, which is quite interesting for human beings and all living beings in this thin atmosphere that surrounds the planet. Then you have CO2, carbon dioxide, which increased quite a lot, as we said a moment ago, since 150 years. But in this case, CO2 is only present on Earth in the gaseous form. It's only gas. There is no liquid CO2 and no solid CO2, which is not the case in Mars, for instance. And then if you introduce extra amounts of CO2 in the atmosphere, then you should increase the greenhouse effect. And you should imagine other processes to reduce this amount through forest or oceans or whatever. Okay, and finally, methane, CH4, which is a byproduct of thermal warming of the Earth because of the thawing the frozen soils in northern latitudes. Okay, so now what are what can be predicted, and how can we predict the future of climate? There are two main methods to make climatic predictions. The first one is numerical calculations, and the second one is based on the theory of critical systems. The first one, numerical modeling, numerical calculations. This is the Earth. In order to perform these calculations, we divide the atmosphere-ocean system into a huge number of elementary cells, which are more or less similar to the pixels in your camera, except they are three-dimensional objects. and you define an initial state for every elementary cell in temperature, pressure, winds, ocean streams, greenhouse gases concentrations, and also the various possible GHG reduction scenarios depending on the decisions of different countries in the world. And then the calculation is run. And during this calculation, every cell here evolves exchanging information with its neighbors and influencing the neighbors as the animals did in the sheep herd, in the sheep flock. And this is done using physical laws. What are the results of these calculations? Well, in all simulations, whatever the GHG injection scenario is, in every case you get continuous increase of temperatures. This is the case where decision makers do not do anything. This is the case where a huge effort is made to reduce CO2 emissions, and these are intermediate cases. But in every case, the evolution is continuous. But you remember the rubber band experiment a moment ago, and here we shall wonder whether how making sure actually that the rubber band would not fail and do not giving something else than continuous evolutions. In order to discuss this point, I need to introduce the sensitivity to initial conditions, which is also called the butterfly wing effect. You have here a billiard table with balls, and you consider the trajectory of this incoming ball here along the green trajectory. It bounces on this other ball here and bounces back again here and so on, and it has a history of bouncing events that may last a long time. Now, if you modify slightly the initial trajectory, the green one, upwards, very slightly upwards, it will change slightly this one and this one, but in a continuous way. By contrast, if you change the initial conditions here downwards, going from the green trajectory to the red one, then you see that something interesting happens here. Instead of bouncing up, the ball bounces down here, and you may imagine that its history, the series of bouncing events it experiences, may totally differ from what it was before. So the history of the ball is totally different. And then if you see that starting with very accurate data, initial conditions in the simulation is quite important, because you can have drastic changes here. Well, so when you want to sharpen the picture in a camera, you just reduce the pixel size. This is well known, and reducing the pixel size increases the number of pixels on the sensor. In the same way, if you want to improve the data accuracy in a simulation, you have to increase the number of cell numbers of cells, or elementary cells on the system, which are equivalent to neurons, as in photography, as in a brain here. But by contrast with photography, increasing the number of neurons also increases the number of synapses, of connections between these neurons. And this increase of synapses is much, much faster than the increase of neurons. This is not the case in your camera, because if you had synapses in your sensor, the images would be terribly awful in quality, of course. And then two different possibilities. Now you try to model the atmosphere evolution. If you do not expect any critical point in the future, there's in principle no computational problem. But if you consider the possibility of a tipping point, then you have huge problems. Actually, as the tipping point is approached, as in the ship flock here, the number of interactions diverges, tends to infinity if the flock was infinitely large. Anyway, in a finite flock, this number of interactions increases enormously, much faster than the number of animals. And if you try to model, to evidence a tipping point using this method, then it should be similar to the horizon, since the simulation tipping point vanishes as we approach it. As we get closer and closer from the tipping point, then you have two possibilities. The computer system may stop working because they would have too many operations to perform per unit time, or you have to simplify, to introduce some simplifications. And in the case of the flock here, instead of having, for instance, 100 animals, you group the animals into groups of 10 animals, and instead of 100 elements, you just have 10 elements. So you reduce drastically the number of interactions, but you lose you lose much information in the groups here, since the behavior of a group of 10 animals is the average of the behaviors of the animals inside the group. So the conclusion is that in such numerical calculations, you cannot describe tipping points. So what to do now? The theory of critical phenomena, of course, and we come back to the fabric I mentioned at the beginning of my talk. You remember that as I was loading in tension this fabric, the fibers failed one after the other, and in avalanches, in small avalanches, some small avalanches, that turned into bigger avalanches and bigger avalanches. And these jolts, these groups of failures are warning signals as a series of fluctuations with increasing amplitudes. This is well known in theoretical physics, and in the case of climate, these fluctuations, these jolts, are extreme heat waves, cold waves, floods, droughts, tornadoes, forest fires, and whatever else. So these are clear signals whose increase shows you, warns you that you are approaching a tipping point. More precisely, this is in this schematic, you have a potential profile here, you have valleys, and our system is sitting here in the bottom of these valleys. It's stable. This is called an attractor, AC, because C means cold in this case. This attractor, if a butterfly flaps its wings in New Zealand or elsewhere, it may disturb a little bit the position of the system here. But since the edges of the valley are quite steep, the fluctuations will be reduced in amplitude. But now we shall introduce more and more CO2 in the system, and then this introduction modifies the profile. And we should get to this position at one time. Here the attractor is still sitting in the bottom of the valley, but two things. First, its temperature has increased as compared to this one, but continuously. If you decided here to turn back to reduce the CO2 content, you should come back here without any obvious problem. And another thing is that the butterfly wing flapping in the other side of the Earth would have larger, more important consequences on the fluctuations of AC, because the slopes here are much gentle, and it means that the restoring force decreases, and then you may have large events, large fluctuations, and you see that these larger and larger fluctuations are a warning sign for the final tipping in the bottom of the next valley, which is now AH, the hot attractor. And at this point, in the same way as the kayaker at the beginning of my talk, if you decide to come back to this point there, the starting point, it would be very, very difficult, because you should reduce the amount of CO2 drastically. And if you reduce this amount to the initial value, that's not enough, because the system will stay trapped in this hot attractor, even if the CO2 content has decreased. And you should go much further back, maybe at the age of Lucy, to restore the right conditions. Okay, so the tipping we expect to happen is sudden, is irreversible, and is announced by larger and larger fluctuations. Actually, the tipping time may be predicted using this equation. I shall not insist on this point, but I would like to say that this equation exists, and if we had sufficiently precise data to introduce in this equation, then we should be able to determine the tipping time. Up to now, it hasn't been possible, unfortunately. Okay, if you want to look again at this process, you may look at this link here on the internet. It's a very short video in which I explain with a sheet of paper and a cork the same thing as here. And therefore, the tipping point should be irreversible. It would bring us in a totally new and unknown state, as at the bottom of the waterfall for the kayaker. The tipping date may be determined, but I think it's too late now to make the calculation if we had reliable data, because the tipping point, my opinion is that the tipping point is already on the way. What should be the temperatures at the bottom of the waterfall in the hot attractor? It should be significantly higher than the popular 1.5 or 2 degrees, much higher, because the process is not continuous, it's a jump into another world. So it may be something comparing our situation to the PETM I mentioned, the Paleocene thermal maximum, in which you had a warming of 5 to 8 or 9 degrees. You should expect something similar. I recommend this paper here, Climate Endgame, which was published last year in the PNAS, the Proceedings of National Academy of Sciences, and they say that plus 6 degrees is not impossible. So now we should wonder whether all what I said so far is serious or not. Should we believe to such theories? You should ask the question to this young lady here, who does not believe in the theory of gravitation, and she's stepping one step more. And this is a good image for climate. My feeling is that we are exactly in this situation. And many people do not believe in these theories. and they are about to proceed one more step, and you can imagine what should be the result. So it's time to conclude now. I come back to the kayaker, and you see that between drifting and tipping, we are obviously going to meet this second state here if we do nothing serious at once. We are in extreme emergency, I should say. We are beyond the extreme emergency. As said Kate Jeffrey, who is a neuroscientist in London and a University College, if you were in a car hurtling towards a cliff, would you say, I'll put on the brakes when I reach the edge, or would you slam them on now? The answer seems obvious. And the point is that for years, scientists have been working, writing reports, publishing papers, giving talks as the one I'm giving now, and all this for nothing. The decision makers did not move at all and do not seem to understand what's happening. And these are no ordinary times, of course, and this is why non-violent civil disobedience actions are being organized by a growing number of people, and essentially scientists. Last November, in particular, in the UK, in Germany, and this is the site in which you could find information about that. And I also recommend a very interesting talk by Jeffrey with the link here, which is entitled Heading to Extinction. To end this talk, I'll just show you three quotes. The first one in the Russell-Einstein Manifesto in 1955, the beginning of the Cold War. Remember your humanity and forget the rest. The second one is much more recent, in 2021, by the International Energy Agency. They said, if governments are serious about the climate crisis, there can be no new investments in oil, gas and coal from this year. And this year was 21, we are in 23. And the last one is by the United Nations Secretary General Antonio Guterres in 2022, last year, including in December, I think. Humanity is facing a collective suicide. So I'd like to end with some hope anyway. Let's keep hope and struggle in spite of everything, or in spite of almost everything. This is an appendix. What to do now? What should we do now? Sorry. A few things to remember and a few possible and non-exclusive emergency measures. I just mentioned these the two first ones here. No new investment in coal, petrol or gas resources. And second, no investment in CO2-free industry, or so-called CO2-free industry, that would not be operational within the next few years, because otherwise it will be too late to prevent us from falling down in the bottom of the hot valley. An example is, for instance, the new generations of nuclear reactors, which are programmed in some countries, and which would not be operational before 15 or 20 years. It's just waste of money. So I let you read the other recommendations here in this slide and in the next slide as well. And this is a bunch of references you may read here, there, and there. And well, okay. So thank you for your attention, and be careful of snakes and scorpions in the future climate state. Thank you very much.